And welcome everybody to today's webinar, Seismic Connections in RISAConnection. So in today's webinar, we're going to be talking about three programs. We're going to be talking about RISAConnection, RISA 3D, and RISA Floor. Now this is going to be very RISAConnection heavy in this presentation. However, we also will be showing a little bit of integration with the other programs. For those of you who aren't aware, we recently released RISAConnection version 5, which includes a number of new seismic moment connections. So for the presentation today, we're going to start off by discussing how exactly some of these connections exist within the code. Then we're going to take a look at working with these connections just directly within RISAConnection, and then lastly, how we can integrate these connections between a complete building model in RISA 3D and RISAConnection. So the codes I'm going to be talking about today are the AISC 36010 and the 341 and 35810. This is the 14th edition of the Steel Construction Manual, the second edition of the Seismic Design Manual. I'm sure some of you out there are still in jurisdictions under the IBC 06 or 09 where you're using the older versions of these codes, the 13th edition and the first edition respectively. So that you're aware, we did not implement the first edition, in other words, the 2005 versions of the Seismic Design Manual. However, the provisions are very similar, and in a lot of cases, provisions that were superseded in this newer version were for important reasons. So oftentimes it's very justified in engineering principle to use the newer edition, even if your jurisdiction hasn't adopted it yet. So let's talk about the types of connections that we have for moment connections in seismic regions. And this would be the connection between a moment frame beam and a moment frame column, where the beam is coming into the strong axis of the column and we have a fully fixed connection. So the first type we'll talk about here is the welded unreinforced flange. And this is a very basic connection type where the beam welds directly onto the flange of the column. And we have these little holes cut out here between the beam and the web to prevent any sort of weirdness occurring in the range between where the moment is attaching to the column, which is on the flanges, and where the shear attaches to the column from the web. So we have a very clear design of moment and axial forces handled through the flanges, shear alone being handled through the beam. And this is just part of conventional connection design for any wide flange member. So in the welded unreinforced flange, or we'll also call it the WOOF-W, we have a shear tab that's welded onto the beam here. However, it's important to know that this shear tab is only used for erection purposes. And for the actual design, you do a CJP weld of the beam web directly onto the column. So that beam web needs to be prepared in order to weld directly fully into the column. And with the CJP weld of the flanges and the web, that beam is fully connected onto that column. And this can be used for the special moment frame, intermediate moment frame, and the ordinary moment frame as well, which I'll be abbreviating as SMF, IMF, and OMF. In addition to that, there's the reduced beam section or RBS type connection. Now in this one, you also have a shear tab, which is only used for erection purposes, whereby the beam can be hoisted in place and bolted on just in terms of the web to hold itself in place for somebody to come in and do full CJP welds for the flanges and the web. Now in the case of the reduced beam section, what we have here is coped flanges. This is also called a dog bone connection. And the reason for the coping of these flanges is to force a plastic hinge to form right in this location. This is most commonly used for special moment frames. It can be used for an intermediate or ordinary moment frame, but this type of connection would be overkill for anything except for a special moment frame. And in this case, the reason for the flange coping and that plastic hinging is that with special moment frames, we expect a considerable amount of ductility out of the system. In order for that ductility to happen, we need to have a plastic hinge form somewhere. By coping out the beam, we can guarantee that that plastic hinge will form right here, which is a good spot for it to be. Next, we're going to talk about the bolted unstiffened extended end plate connection, the BUEEP. And this is where an end plate is welded onto the beam. This type of connection is convenient because you don't have to have those temporary erection devices. You can actually bring this connection right up here and just bolt it onto the column in the field with this plate pre-welded onto the beam end. And in this case, for the unstiffened variant of this connection, you would have 4 bolts per flange, and the beam is just going to be CJP welded directly onto that end plate. Now, there's another version of this called the stiffened version of it, the BSEEP. And in this case, you can have either 4 bolts arranged like we showed here, or 8 bolts per flange. And either way, there's a stiffener that comes up. This is a stronger connection type. It's a little more expensive to use, but sometimes it's necessary, as we'll see in the program here. And the other ideas behind this are completely the same. And then we have the bolted flange plate connection. With the bolted flange plate connection, here we can actually get away with a fillet or PJP weld. So this is the only connection type that doesn't involve CJP welding. And you can do that onto the web there, although the flanges still do need to be CJP welded in this case. So this is just another connection type that we have available. And all of these connection types existed in the prior versions of RISAConnection. However, in the latest version, we can also use these as seismic connections as opposed to non-seismic connections. Now, what do I mean by non-seismic connections? Well, this would be in the AISC 7 what's defined as systems not specifically detailed for seismic resistance. And in this case, you can use an R of 3, and this allows you to get away with using only the AISC 360 provisions. So all these moment connections that we showed you here just now, with the exception of that reduced beam section one, could commonly be used in structures that are controlled by wind forces, for example, where we need everything to stay in the elastic range and we're not trying to force ductility into the system. However, a limitation here is that these types of systems are not allowed for seismic design category D and above. And so anything with any decent amount of seismic in the structure, you're not going to be able to get away with this R equals 3. The code does not allow it. And so in that case, you have to start delving into the seismic moment connections. So we'll start with the ordinary moment frame, which is the lowest level of the seismic moment connection. You'll note that the R here is 3.5 as opposed to 3. Now remember that the R goes in the denominator of the seismic base shear equation. And so a larger R value is going to decrease your amount of seismic forces. As you can see with the OMFs, though, you're not decreasing the seismic force by all that much between an R equals 3 versus an OMF. Now also note that the ordinary moment frame is not allowed for seismic design category D and above. So you might ask yourself, why would the ordinary moment frame exist? Well, the ordinary moment frame is actually allowed in certain single-story structures. So if you have a one-story building meeting certain requirements in the AISC 7, you can actually use an OMF. And bear in mind that an OMF is different from a no seismic detailing frame, an R equals 3 frame. This is something that doesn't exist in concrete, so some engineers who are more familiar with concrete than steel tend to think of an ordinary frame as one that has no extra detailing. However, an ordinary moment frame does actually have extra detailing that's required above and beyond the ordinary AISC 360 code. That's the 14th edition. It has some AISC 341 provisions which must be met. So in the case of an ordinary moment frame, you essentially have 3 options as to how you want to design this. The first is that you can design the moment connections in that frame to have 10% more strength than what the beam has. So that ensures that even when the beam hits full yield, or even all the way up to full plastic yield in this case, since the beam is typically designed for 0.9 times F times Z, the plastic modulus, your connection will still be 10% stronger than that to ensure that you don't get a failure in a connection. Because during an earthquake, connection failures have been proven to be the problem with buildings collapsing. We want that failure, if it's going to happen anywhere, to be in the beams. So option number 1 is just design those connections so much stronger than the beam that there's no way that they're going to fail. That can be difficult, though, to get a connection that's that much stronger than the beam, especially when you consider the idea that even a full CJP weld is still only going to be able to develop the beam's strength itself. The second option is to design the beam to remain elastic at full earthquake force. Now, this is rare. Keep in mind that an R equals 3, essentially, because that's in the denominator, is reducing the base shear for the seismic design to be 1/3 of what the earthquakes will be. And that's to account for the fact that there will be some amount of ductility in the system. Something's going to yield somewhere that's going to release some energy. However, with an OMF, we can design for a seismic base shear using an R of 1, which is a huge amount of force. But if you beef up your beams and columns and connections so large that they'll actually pass normal code checks at R equals 1 earthquake levels, then you're allowed to get away with that because your whole system is going to remain elastic even under these tremendously large forces. Now, of course, these forces would be tremendously large under a seismic design category D, for example, where we're talking about taking advantage of this exception here for the single story structures. But ordinary moment frames can be useful for lower seismic design categories where your base shear is so small that even if you triple it by using an R equals 1 instead of an R equals 3, you're still going to have relatively small earthquake forces. And that would be for places like the Midwest, for example, in the US. Now, your third option for an ordinary moment frame is just to CJP weld everything. And in this case, you need to meet a number of different special moment frame provisions and AISC 358 provisions. And these provisions that you have to meet are nearly as stringent as the next system we're going to talk about, intermediate moment frames. So therefore, people don't commonly do this, since if you're going to take advantage of this third option, you're just a short step away from being in an IMF. Now, in an IMF, your advantage is that your R jumps up to 4.5. So that means that your forces are only going to be about 2/3 of what they would be in an R equals 3 system. And so that definitely helps out in terms of the demand on things. Now, the IMFs are also not very popular, but they're used in certain circumstances. They're not allowed for your seismic design categories E and F, except for in certain single-story structures. So you're taking a step above the OMF. However, you also can't use an IMF for a high-rise building in seismic design category D. So there's a certain height limit to how high you can take these up. And in the intermediate moment frames, you have to meet provisions from AISC 360, 341, and 358. So you have 3 different codes that have provisions that have to be met. However, you do have some relaxed provisions in AISC 358, such as span to depth ratios is a good example. There's a number of other individual provisions where it's not very stringent as compared to the special moment frame. And for any sort of high seismic situation, especially if you're getting into seismic design categories E and F, you're probably going to end up in this special moment frame. Now, you do get an excellent bonus from the special moment frame in that your R is 8, so your seismic forces are greatly reduced. However, you have very stringent provisions in the AISC 358 that have to be met relating to things like welding, for example, in order to achieve this special moment frame. So let's take a look at what this means practically within the program. For that, I'm going to open up RISAConnection here, and we're going to take a look at a sample connection of an extended end plate. So this is the bolted extended end plate, unstiffened connection. Now, in RISAConnection, you may have used this before, and if we come over here, there's a new setting here, seismic system. And if seismic system is set to none, this would just be an ordinary wind type connection here, and this just meets the AISC 360 provisions. But in this case, we're going to take a look at this under seismic system as an OMF, ordinary moment frame, bolted extended end plate. And here we have some extra input that we need to put in relating to the code. So, for example, shear due to gravity, VG. So we have to input this in, and we can take a look down at the bottom of the screen at any time to see what this is referencing. So in this case, beam shear force resulting from the 1.2 times dead plus live plus 0.2 snow gravity only load combination. In other words, some of the calculations that need to be done need to know what the gravity shear is as opposed to the seismic shear, so that we can use the difference between those to know how much shear is coming only from seismic forces as opposed to gravity forces. We also need to know the clear span of this beam from flange to flange on the columns. And we need to know what the maximum moment that can exist in this connection is. Now this is different from our design moments down here. So our ordinary design forces would be 100 kips here for shear and 1,000 inch kips for moment. And let's just say that those are the forces that would be derived using our seismic base shear equations, where we're using the OMF that has an R of 3.5. But keep in mind here that the code says that if we're going to do this as an OMF, if we take that second option that I showed earlier, that we actually need to do this using an R of 3.5. So if we want the system to remain entirely elastic throughout this, we need to design for forces that are 3.5 times what the seismic base shear would tell us that they need to be. In other words, instead of 100 kips, we need to design this for 350 kips of shear and 3,500 inch kips of moment instead of 1,000 inch kips of moment. Now, this is a tall order, but we can actually make this work in this connection type. So let's take a look at this connection as it currently stands right now with this existing design. If I come into the reports here, we see that a number of different things are failing within this connection. Now, if we scroll down a little bit, we're going to see a number of passes and fails. We'll also see some other interesting things in here. So seismic moment at face of column. In the case of an ordinary moment frame, this is just a direct input of the 3,500 inch kips that we need to design for. But we also see some NAs reported in here. So under seismic width to thickness ratios, we can take a look under here, and this is the limiting width to thickness ratios per AISC 341. And we see NA because this limit state is actually not necessary for ordinary moment frames. Now, this must be checked for higher levels, such as IMFs and SMFs, but for the OMFs, it's not necessary. So what we do in RISAConnection is we report these things to you, such as the column beam to moment ratio, so that you're aware of them. But this is just for your own reference. This is not needed to be met for a pass-fail check. And so we can see some of that down there. Now, coming up here, let's take a look at some of the limit states that might control on this one. So I'm seeing, for example, seismic end plate flexural yielding. And what we see here is we've got a demand and a capacity, and in this case, 201 kips of demand, 132 kips of capacity. So this is 50% overstressed. If I click on this, we can see here the code equation, AISC 358, and we can see on this equation right here what goes into the strength calculation for the seismic end plate. The one thing I'm noticing here is that we're using a 36 KSI end plate, and that's probably going to not work out too well for us. So let's go ahead and bump that up. I'm going to come out to the 3D view and click on this end plate. And here, we're going to pull up a grade 50 for the end plate. So if I click on it and just change the grade and then come back in here, we can take a look at how that has then affected this. So if I go to end plate flexural yielding, we'll see we're now only about 9% overstressed instead of 51% overstressed. So we also need to come in here under the thickness, and let's go ahead and bump the thickness of that plate up to 7/8 of an inch. So we've got a little bit thicker end plate on there, and now our end plate flexural yielding is passing. So we're on our way to getting this connection to work. Next, we'll take a look at the bolts in here. If I come back into my reports, we're going to see that we're failing for bolt shear, bolt bearing. So I probably need to increase these bolt sizes. I'm going to click on the bolts right there, and we'll change them from a 3/4 inch to a 7/8 inch bolt and go back into the reports. But we can see there's still 3% overstressed. Not much, but we certainly wouldn't want to print something like this out and hand it in to somebody showing that we have an overstress, even if it's a small amount. So I'm going to click back on that bolt, and I'm going to change the grade from A325 to A490. So at this point now, we're passing for the bolts. But if I come down a little bit further here, we're going to see that we have some seismic plate limitations that are not being met. So thick plate behavior. In other words, we need to ensure that the plate that's going to be on here is not going to be undergoing any prying. So if we get a tension force on either flange, and remember that in seismic connections, these forces are reversible, so either flange could be the tension flange. We want to ensure that this plate is not going to pry around these bolts. And one easy way that we can accomplish that is to add in stiffeners. So if I choose to add stiffeners to this connection, that is now going to eliminate that thin plate behavior that we were experiencing on there. And so we can see that's listed as a pass now. However, the column flange is now saying that the column flange is going to get excessive bending. We're not getting a thick column flange behavior in this case. So let's go into that column, and I'm going to add in transverse stiffeners. And so when I choose that, now we have these stiffeners on here. And we can come down and find out that now we are actually achieving what we were trying to under the seismic plate limitations. Oh, well, we're actually not nearly doing that. And the reason for that is that the column flange flexural strength is inadequate. And actually coming down here, we can see the reason why the seismic stiffeners, in other words, these transverse stiffeners that we put in here, some people call them continuity plates, are failing. And so we see that under compression, they fail. And so if they fail, we've discounted those stiffeners. We're not considering them to be active as part of the flange bending capacity. So what I probably need to do is come in and bump up those stiffeners. I'm going to click on those and bump them up to a 1/2 inch thickness. So at this point now, the stiffeners now pass, and because the stiffeners pass, then we also get a pass on the seismic plate. So everything passes in this connection at this point. So we can see all we had to do was bump up the plate thickness and grade, add some stiffeners, bump up the bolt diameter and grade, and put in these continuity plates. And now we've actually met all of the seismic provisions for AISC 341 for the ordinary moment frame. Next, we're going to try out this exact same connection as part of an intermediate moment frame to see how things are affected there. So I'll click on IMF, and you'll see instantly that the input changes. We no longer need to input that 3.5 times value for the seismic strength. So we're no longer considering this as something that needs to remain elastic during an earthquake. We can now actually allow certain parts of this system to get plastic deformation during the earthquake. So if I come back and take a look at this now, we're going to come down here and see that some things are failing. Now, by going to a intermediate moment frame, we have some more stringent provisions, but also you'll note that our seismic design force for the connection itself is greatly increased. So before, whereas we had to design this for 3,500 inch kips, now we're actually having to design this for 5,500 inch kips. But this is no longer a user input. Instead, what happens is that the maximum probable moment at plastic hinge is calculated. And what this means is that the program is determining where the plastic hinge will form on the beam for this connection. And then in this case, it's able to figure out what the maximum moment that could be transferred through this interface could be, as both the moment and then also there's a shear component that goes into this as well. Now, this is one of the more difficult things to calculate by hand out of the code. And so it's very convenient in this case that RISAConnection is calculating this for us. But we can see as a result of that, and as a result of some other code provisions, which we were allowed to ignore for OMF, now we're getting some failures in this connection. So let's take a look at the seismic bolt moment strength. So those bolts that we bumped up before that were adequate are now failing by 30% using the provisions of the intermediate moment frame. So I'll go back to these bolts, and we'll take them from 7/8 all the way up to a full 1 inch diameter in this case. Then coming back, we can see that those seismic bolts are now passing. Next, let's take a look at the seismic plate. And once again, we're getting a thin plate behavior in this case. And so we need to come back into this plate, and we need to also increase its thickness once again. We're going to go all the way up to a full inch thick on this plate. So the plate's getting a little larger, the bolts are getting a little bit larger, but this is allowing us to go into this IMF, which would allow us to use this on more buildings that are in higher seismic design categories. Now, the seismic stiffeners as well, I saw, were also failing in this case. So we had bumped those up in size from 3/8 to a 1/2 inch before, but now we're still getting a failure in those stiffeners. So I'm going to click on these stiffeners, and we're going to increase them yet again. Let's take these all the way up to 1 inch. All right, so we've gone up to 1 inch, and at this point, the stiffener capacity is actually passing at this point. But let's go back and take a look. So we're talking a full inch thick stiffener welded onto this column. And I probably don't need to tell you that this is a rather absurd detail for a connection. I don't think anybody's going to want to actually put that in here. So let's go back in, and instead of relying on the stiffener to handle everything, let's beef up these column flanges so that they can take a little bit more forces themselves. So I'm going to click on the column, which is currently a W12 by 58, and let's try out a slightly larger size, a W12 by 72. So in this case, now the stiffeners are actually still not quite adequate at that 1/2 inch size, and we're getting a couple of other failures. So let's come back into this column and make it larger. In this case, I'm going to make it a W12 by 79. And if we do that, that solves all of our problems right there. And that's something that you'll find in a lot of these seismic moment connections, is that the columns end up becoming a very limiting factor. So more often than not, you need to have some pretty heavy duty columns in a seismic moment frame in order to meet the intermediate and special moment frame provisions. Next, let's take a look at this as a special moment frame. So we're going to bump this connection all the way up to be an SMF at this point. And we can see right away that now, once again, we have a bunch of failures because, of course, we need to go even larger with some of these things to meet the SMF provisions. So you can see where these SMF connections are more expensive than their typical OMF counterparts by having to add in these extra things, but we're making up for that by having more ductility so our R value decreases. So in this case, I'm going to click on this column right here, because if we go into the reports, what we're going to see is that we're failing for seismic column panel zone shear, among other things. And so we need to have a panel zone which is going to be larger to do this. Now, in order to take care of that seismic panel zone shear, we could put in web doublers on this connection. However, all of that extra welding and detailing is going to be very expensive. And so instead, let's go ahead and try out using a larger column size. Now, in this case, I'm going to bump it up a fair amount, a W12 by 152. But in this case, by going all the way up to this much larger column, we now have everything passing perfectly in this connection, whereas it was failing by 80% earlier. Now, one of the advantages of going to one of these large, heavy columns like this is I can actually come in at this point now and remove these transverse stiffeners that we needed on the other connections. And I can pull those out and still meet all of the code requirements. And so in this case now, we're still passing with everything. So I have what's called a clean column. We don't have to add any stiffeners onto this column, and our fabricator is going to thank us for that, even if the weight of the steel ends up being a bit more heavy. So now you've been able to see this connection evolve through the OMF, the IMF, and the SMF, which should give you somewhat of an idea of how, as we bump up with each connection, our requirements from the code become more and more stringent. And we can see right here a listing of all the different checks that we're doing, by the way. So here you can see all of the ordinary checks, as it were, the non-seismic ones. You'll note that these don't say seismic in front of them. So these would all be per the AISC 360 or things of that nature. So if I come in here, we can click on those. Now, the ones that are listed as seismic, basically everything from this line down, these are all part of that AISC 341 and 358 checks that need to be done. So now that we've seen how to use these connections within RISAConnection, next let's look at how this can be used not for just a one-off connection design, but to actually get a design for all of the moment frames within a building. So for that, I'm going to exit out of the program, and I'm going to open up RISA 3D instead. And so let's take a look at this RISA 3D model that we have. In this case, this is a several-story frame building where we have concrete moment frames down at the bottom with steel moment frames coming up from there. And in this case, I have some braced frames running in the global Z direction, and I have moment frames running in the global X direction. So in the program, one thing that we have to do is come up and take a look at the codes. And so if I go into the global parameters and take a look at the codes here, we'll see that I'm set to use the AISC 14th edition LRFD. Now, for those of you who aren't aware, for the intermediate and special moment frames, you are not allowed to use ASD. So you need to go to LRFD if you're going to be doing these designs. So I want to make sure that my codes for both the hot rolled steel and the connections are both set to the AISC 14th edition LRFD. So with that set in place, the next thing that I'm going to do is come in and take a look at my seismic design rules in this structure. So if I come into seismic design rules, you'll see from this spreadsheet, we have several predefined seismic design rules. Although don't feel that you have to be held to these, you can hit enter in any of these spreadsheets and add additional rules as you see fit. In this case, we happen to have a predefined rule called the SMF RBS, and this has a high ductility. In other words, this would be a special moment frame as opposed to an intermediate or an ordinary moment frame. And if we take a look at the beam requirements for this SMF RBS, you'll see that in RISA 3D here, we would define this as having an RBS connection, although you'll see all the different connection types are available in here. In this case, overstrength is not required for the design of the beam because remember that RISA 3D is focusing on our member design for things like the beams and the columns. It doesn't care about the connections. However, we are having a hinge factor. Now this hinge or this Z factor in this case, this is related to the RBS in particular. And what we're saying with this 0.75 is that at that reduced beam section, or in other words, the location where we've coped out that beam for the dog bone, that the Z, the plastic modulus of the beam, is 3/4 of what the full beam would be in this case. So we have a 25% reduction in plastic modulus by coping out those flanges. That's what's creating that weak spot in order to form a plastic hinge. And then also in the program here, we can specify the location of that hinge. In this case, this would be 14.625 inches away from the face of the column to the center of the hinge. So this information needs to be predefined, and you can take a look in the code to get ideas of how to estimate this information. And then what we can do is take this into RISAConnection to get more exact information. And we may need to go back and forth a couple of times in order to get all of these things lined up with Z factors and hinge locations that work for us. But hey, nobody said that seismic design was going to be that easy. So the next thing I'm going to do is come in here under the members, and I'm going to color code these according to seismic rules. And what you'll see is I have these 4 moment frames defined here. And in this case, I have assigned the SMF RBS connection to those. So if I double click on one of these beams and come in here under the design tab of that beam, you'll see that we can assign the seismic design rule to these. And some of the other members have none, which basically means they're not being designed for seismic. So those will be ones that are part of the brace frame in the other direction or the concrete members down below. Now, bear in mind that both the beam and the column need to have this seismic design rule assigned so that the program recognizes, hey, these purple frames right here are what are my seismic frames, my moment frames in the X direction. So I have those predefined already. But at this point, we now also need to put connections on those. To do that, I'm going to open up the connection rules spreadsheet out of the data entry toolbar. And here we can see these are a number of different connection rules that can be used between RISAConnection and RISA 3D. Now, something that a lot of people also aren't aware of, what you're seeing here is just a small sampling of the number of connections that can be brought back and forth between the programs. This spreadsheet is just sort of a default spreadsheet in the program. You can add as many lines as you like in here and add all sorts of additional connections that aren't set in there as the default. So never be afraid in any of the spreadsheets in the program to hit enter and add your own lines. You don't have to use the default ones that ship with the program. So right on here, I'm going to create my own connection rule, and I'm going to call this my seismic moment connection type. And in here, we have to choose whether these are going to be a shear connection, a moment connection, or a brace connection. Obviously, moment is the type that we want. And then I can come over here to this drop-down list where the program is now going to list every single moment connection that's available to be integrated in between RISA 3D and RISAConnection. And in this case, I can take a look here and find the column beam seismic moment connection. Now, you might be asking yourself, how does the program know which connection type I want to use? If I'm just saying seismic moment, how does it know whether I want to use an RBS or a BUEEP or a WF, any of those different connection types that I showed you in the PowerPoint at the beginning of this presentation? Well, the way it knows that is that when I assign this connection to a given beam, it's going to take a look at the seismic design rules for that beam, specifically right here under the beam tab of the seismic design rules spreadsheet, and it's going to look at what moment connection type I specified in here. So in summary, we assign just a generic seismic moment connection to all the beams, and then we use that beam seismic design rule to get into which specific connection type that we're going to use. In this case, we're going to use RBS on these. So what I need to do now is assign that connection rule to these beam types. I'm going to unselect the entire model, And I'm going to come in here and use the criteria select tool on the left, which will allow me to select only certain items. And in this case, I'm going to come under the Members tab. We're going to come here and say that we want to grab all members that are type beam, that's as opposed to column or brace. And I want only members that are assigned to this SMF RBS seismic design rule. And if I hit select members, you'll see now only the beams that were assigned to that seismic design rule get selected. Next, I'm going to come up here and go to my modify members. And under modify members, we can come over here under RISAConnection and choose that seismic moment connection. And I'm going to check the use box for each of these and say apply to all selected. Now, of course, I don't get a visual verification in this case because I'm color coding by seismic design rule. However, I can color code the member ends by coming up here and saying, show me the member ends by design or by connection rule. And you'll see now that each member end shows a seismic moment connection listed there. So with that all set, we'll come up here to insert seismic load. Now, in this case, we actually have a diaphragm defined at each floor level, so we're able to get the automatic seismic load generation. We're going to generate these loads per the AISC E7 2010 using an R of 8 because we're a special moment frame in this case. So I'll hit OK on that. And then we'll come into the load combinations. And in this case, I generated load combinations for both directions, for both overstrength and non-overstrength. Because bear in mind that some of these connection details and the such need to be designed for overstrength forces. That's these omega level forces, also known as the amplified seismic load, as opposed to the non-overstrength. And all of this can be done directly through the seismic LC generator right here. And this is what I use to generate all these load combinations. So you'll see in this case that we've got 17 different load combinations. And I'm going to solve a batch and envelope solution of those. And once that finishes solving, then we can come out here and actually get our connection design. And so for that, I'm going to come up to the director up here and choose RISAConnection. This is going to bring all this information, including the member end forces for all 16 load combinations. The first one doesn't count. We're going to bring all of those into RISAConnection. So I click on RISAConnection here. All that information is now brought over, and we see a folder here showing an RBS connection type, as well as a listing of every single member from the RISA 3D model that had that connection. So here we're actually going to be able to mass design all the connections as opposed to having to fiddle with them one at a time. So the first thing that I want to do is do a solve project right up here in RISAConnection that will solve all of the connections in my project. And let's just take a look right here on the right, and we see fail for the group. This is our group of seismic moment connections, and what it's saying is that at least one of them failed when we get that reported. And then if we look in the tree below, we'll see a listing of each connection, and we'll see a failure for each one. So let's just jump straight to our first one. So this is this beam M10 right here, and we see we're getting a failure. If I come into the reports and scroll down here, one thing that I'll point out on the right side is that the program knows that this is an SMF RBS. It brought that information in from RISA 3D. It knows the shear due to gravity. It knows all these other entries in here. So it's aware of what the Z factor is that came out of RISA 3D and the hinge location and the clear span. It has all that data. And then it also has my shear and axial and moment forces per load combination. So I'm able to get a design for each individual load combination as opposed to getting an envelope design of all load combinations. Some other connection software out there will actually just design for the maximum shear, maximum moment, and maximum axial force occurring simultaneously. But of course, we know that could be terribly over-conservative for some designs. Anyhow, coming over here, we can see for this connection that I'm only getting one fail out of all of this, and that's right here under the Seismic RBS connection detail limitations. So let me click on this, and what we'll see is I'm getting a fail under this check A and check B. Where do A and B come from? Well, thankfully, the program will show us right here that we could just take a look at AISC 35810, equations 581 and 582, and that would explain those to us. But in case I don't want to crack the book open, I can also just take a look at a text description of what each of these are. So in this case, A, The horizontal distance from the face of column flange to the start of the RBS. Well, I can see that graphically if I go into a 2D view. That's simply this dimension right here. So from the face of the column flange to the start of the cope, that's 4.37 inches. We're getting a failure on that. And then if I come back into the report again and take a look at B, this fail right here, we're seeing the length of the RBS cut, 20.51 inches. And so this needs to be between 65% and 85% of the beam depth reported right here. So based off of this, it looks like actually we could just use a 20-inch value for that B and fall directly within there as opposed to this 20.51. The 20.51 was just a guess by the program when we came over from RISA 3D as to what we might want to use, but we may need to tweak this a little bit. In this case, if I click on that dimension and type 20, now we can see my results have been cleared. But if I come into the reports here, I can hit solve connection, and that will resolve this current connection. And now we'll see that we actually pass in here. So all we need to do is remove about a ½ inch out of this in this case, and now our A, B, and C are all adequate. So each one of these connections has been laid out, if we come and take a look at it, with that 20.51. So this is something that I would want to change for all of my seismic moment connections. Obviously, a typical detail is going to be great on a project like this where I have so many different connections to manage. In order to do that, I'm actually going to click on the group up here at the top. And so for the entire group, if I come down here on the right, we can see I can take a look at the group properties. And if I go to the RBS connection dimensions, you're going to see that I have various listed down here for this A and B. Well, I'm going to set this B to be 20 inches for all of these, and that's going to set the A to be 4 5/8 inches. So now every single connection has now been switched over to use that 20 inches. We could just do that all at once. Then I'm going to hit solve project again, and that's going to come in, and we're going to see that some of these connections are now passing, but some are still failing. So if I click on this failing one, for example, and we take a look here, let's just take a look at what this connection is in this case. Now, this plate may look a little goofy in this case with these 4 bolts, and it's this full height in this case. Bear in mind, though, that that plate is only an erection plate. In this case, these bolts are only going to be used to put this beam up. This CJP weld, which you can see on the backside here, is what's actually going to be doing that shear transfer. Let's go into the reports here and take a look, and we can see here we have a seismic column panel zone shear failure. And so we're slightly over on the columns. One option I would have would be to bump the column sizes up. But let's say for some reason we're locked into this column size in this case. Well, in that case, what I can do is come in and tell the program that for all of these columns, I want to use web doublers. And so when I choose that for the group, you'll see that the individual image for each one of these now shows a web doubler for each one. And if I click on this column here, we can come in and see a single-sided web doubler, since I didn't need it on both sides, has been added in. However, we are getting a failure in this case under seismic panel zone limitations that's showing that the doubler thickness is inadequate. And so in this case, if I come back and take a look at the doubler that we used, this is just a 3/8 inch thick doubler. Let's go ahead and bump that up to a 5/8 inch doubler and see if that's adequate. So in this case, that passes. So now I'm going to go up to the entire group and make sure that all of our doublers that are used here, as opposed to various, are using a 5/8 inch thick doubler. And I solve again, and we now see pass listed for every single one of these connections. So now we can see that I have one typical detail in this case, this exact design that we have here, that's adequate for every single seismic moment beam in my entire building. And furthermore, that's being considered where we have every single load combination, in this case 16 of these, considered for each one of these connections. So we've got whatever this amounts to be, 16 by 20, that's hundreds and hundreds of different permutations of this, and it works for all of them. So we can have confidence that this design is going to be adequate for everything. So now I'm going to save in here in RISAConnection, and I'm going to choose to export this out to RISA 3D using the Export to RISA 3D button. And so with RISA 3D here now, we can come in, now that we've brought in these connection results, and graphically review them. So I'll take a look at the member ends under connection results, And we're going to color code all the members in the RISA 3D model as either green or red based off of pass or fail for their connection. And so right here, I can see all of these members shown as green in this case, and we're getting this 0.997, 0.983. That's the controlling code check for each one of those connection members. Now, in addition to this, some of this information is repeated in both programs, so I can access it in either location. So if I take a look at one of these beams, for example, let's just take a look at this one right here, this beam M9, and I come down and take a look at its detail report. What we can see here is that I've got my AISC 341 and 358 checks being done on the beam. So in this case, the RISA 3D is checking this to make sure that the flange and the web are seismically compact. It's checking the column to beam moment ratio, required flange strength, so on and so forth. It's even figuring out the required connection moment strength based off of the probable moment and then the plastic hinging that's occurring. And it's comparing those against my overstrength forces and using whichever one controls out of there. So for member M9, as an example here, we can see that the demand is 1,009 kip feet. Well, I can also see that in a different level of detail directly in my RISA model right over here, where in this case, if I track down member M9 and take a look at the reports under the moment demand for this connection, right here, seismic moment at face of column, 1,009 kip feet. And here, as opposed to RISA 3D, where we just get sort of a summary report for the entire member, we can get it in a great level of detail reported directly out of RISAConnection here. So this just shows how RISAConnection can complement RISA 3D very well in terms of showing us a great level of detail for the seismic connections. So we've seen now how we can put together a individual connection one at a time in RISAConnection just to get a one-off design, or how we can actually get design for an entire building very easily and meet all of those very complex code requirements. And so that was the intention behind RISAConnection version 5, was to make all of this much easier to do for the engineer.